Alright.
You are visible, you are audible, your presentation is
Hello.
also visible.
Good afternoon, everyone. Welcome to this session, which is one of the most practical and widely used tools. So, we'll be going with. We'll be starting with the tools that are most widely used in engineering. That is the PID controller. Whether you're working on robotics, drone, or even on your phone camera, PID is everywhere. Today, we are going to understand what it is, how it works, and where it is used in real world. So before that, I'll be talking about EYRC. So that is the e-Yantra robotics competition. So in this competition, where we have a lot of domains that are being played. So basically, the drone domain, then control systems, and ROS and FPGA, where you get to learn a lot of things about it. So this is the timeline of UIRC, which is basically 7 to 8 month long competition. It is divided into two stages, that is the stage one and stage two. This is the timeline which you can follow. This take a look at the things which are in UIRC. So this was basically what do you get in this competition? So you get e-Yantra certificates, cash prizes worth 10 lakhs, e-Yantra goodies, and 8 week paid internship at IIT Bombay. So this is this year's registration. So you can go to portal.e-yantra.org to register for your team and get a chance to participate in this competition. Also, there is a MOOC which is based on ROS 2. So the registration date has been extended to till July 26th, 2025. So okay. So now let's get back to the topic. So we'll be starting with PID. So PID is basically a like we have closed loop system, so it is kind of feedback that has been used. So let's begin with basics. A control system is any system that tries to get an output to match a desired input. So let's just think about a cruise control in car. So we want to maintain, let's say, a speed of 60 kilometers per hour. The car needs to respond to changes like slopes or wind. So the controller decides how much to accelerate or deaccelerate. So without feedback, the system is basically called an open loop system. With feedback, where the system continuously compares actual speed with the desired speed, it becomes a closed loop system. PID is a closed loop controller. So, so in PID, P, I, and D are three different terms. P stands for proportional, I stands for integral, and D stands for derivative. So now as we see, so here's the basic block diagram of PID, where um, where you see there is something known as reference, that is nothing but a set point, that is basically the desired input or the target value of the system. For example, in a temperature control system, this would be the desired temperature you want to maintain. And in cruise control, it would be the target speed. So the plus and minus sign that you see over there is called as the summing junction, where the error has been calculated. So it takes this reference signal as the input, and then subtracts the output to determine the difference between what is the desired and what is the currently being achieved state. So then comes the PID controller. So in this particular diagram, PID is the brain of the control system. So where P stands for the proportional, I stands for integral, and D stands for derivative. And the plant represents the system or the process that you want to control. This could be a motor, a heater, a robotic arm, a vehicle, or any physical system whose output needs to be regulated. The PID's controller's output acts as the input to the plant, influencing its behavior. So then the feedback loop. The feedback loop is nothing but the output of the plant is fed back to the summing junction. This feedback is crucial because it allows the system to continuously compare its actual performance, and then we finally get the desired output. So now coming back to the introduction. So PID is not something that is, that is very sacred or something. Everyone has certainly seen PID in like practical applications. So now let's consider PID is basically used to keep the like physical quantities to be stable, like maintaining a stable temperature, like your room can maintaining a temperature in the room, the cooling temperature. So for example, you want to keep your temperature constant at 24 degrees Celsius. So you turn on the AC. So you keep the temperature till 24 and all. So now out of that, a question arises that why do we need PID when, like for example, if you have a heater, so you have to keep the pot temperature to 50 degrees, and like why do you need the calculus and mathematical equations for that? So yeah, so basically for maintaining 50 degrees, or like just you can, if the temperature rises above, you can just cut off the power and you will get the output, right? So yeah, so that is actually correct. It can be done in that manner, but now consider, what if you want to do that with car? So you want to, you have want to maintain the speed at 50, and your speed goes up to 55. So that would be quite brutal to directly turn off and get the control of that. So these are the conditions where you need a smoother control over, and that is where the PID plays a vital role. So so there are basically, as we saw, so there are basically four modes which we can term as. So the most common modes are the on off, that is the bang bang control, and then comes the proportional control, then comes proportional plus integral, proportional plus derivative, and then comes the altogether PID, that is proportional plus integral plus derivative. So now we'll talk about what is on off control. So, imagining heating water. If the temperature is below 50 degrees Celsius, you can turn on the heater. If it's above, you can turn it off. This is basic example of an on-off control, which is actually crude and causes fluctuation. Now imagine a drone trying to maintain a height using on-off control. It would jerk up and down constantly. That's where we need something smoother and intelligent. So okay, so now you can see your image on your screen. So like visualize with that. So this is a temperature versus time graph, which is using on-off control. So we can see a constant oscillation at the target temperature. So this is because the system keeps toggling between on and off and anticipating the trend or the error accumulation. So so now coming to PID. So PID stands basically proportional integral and derivative. So as I said, we can use four different things in this, just the PI, PD, and PID. So P handles, so the basic ideation behind that is P handles the present, I handles the past, and D predicts the future. By combining all three together, you get a fast, stable, and accurate control. So the block diagram that you see, so uh, this is the reference is been fed back to the error, and and then it is given to the P, I, and D with each with different gains, that is KP, KI, and KD, and accordingly it is fed to the system. It adjusts the output accordingly, and it gives the input to the plant or the process, and then the new error, that is again the feedback loop as I explained earlier. So the feedback loop comes back together and it's fed back to the error, and then the process starts working. So let's break down it all together. So P it's nothing but the one that reacts to the current error. Larger the error, larger will be the correction. So in this, basically P is nothing but P is multiplied with its constant Kp to find an output. And in PD, so Kd is been differentiated with Dt. So P and D are been altogether done, and you find the output with that. So PI. So now when do you use PD control? So PD is used in systems where predictive damping is important, but you don't need to eliminate long-term error. Example, a robotic arm movement where the movement is faster. Smoother response, you require a smoother response as it won't damage your. Then comes the another pair, that is PI. So PI is required when you have to eliminate the steady state error. So example, a temperature control in a heater or oven. So now why do you need the combination of all three? So the combination of all three is used in the system where you need precision, stability, and minimal error. For example, controlling the drone's altitude. So now coming back to one more next, the performance of this. So now we can see. So let's understand two important concepts here: state response and steady state error. So state response is nothing but how a system reacts when you suddenly change the input, like flipping a switch from 0 to 1. For example, imagining asking a robot out to go from 0 to 90-degree instantly. The weight accelerates, overshoots, oscillates, and eventually settles. Shows the steady set. Shows the step response, like what is this behavior. And steady state error. Steady state error basically is the difference between desired value and the actual value after the system has settled. Ideally, this error should be zero. But for example, if you consider a heater to reach 50 degrees Celsius and it always settles at 48 degree, so that the 2 degree that you find is your steady state error. So now, as you see, the chart shows the with P, but never it's never not near to the target. With D, with I, eventually with PI, you eventually reach the target, but it might overshoot. and with the combination of all PID, that is the red color, you can see here that you smooth out the overshoot and you get the desired out. So let's see a video which shows the live tuning. So there are three particular sliders. This slider shows your KP, this shows the KD, and this shows the KI. So after toggling them, you can see what output do we get. So now, so the basic tips for designing a PID controller. When designing a PID controller, like we have to keep certain things in mind. So we start with KP, increase the KP until you get a fast response, but you have to watch for the overshoot. So when you finally see a overshoot, that is when you have to stop like increasing the KP. Then what to do next after we see overshoot? So when do you see overshoot, you can slowly like add Ki. So what Ki does is it removes the steady state error. So that is where you need to add Ki in that. Then you add Kd to dampen the oscillations and dampen the overshoot. So now you can plot your system's response. Like observe, we can observe the rise time, you can also observe the settling time and the steady state behavior. So if the system becomes unstable, we can reduce one or the more gains. Also, so one thing you have to know your system's dynamics, like how fast it is or how slow system needs the different tuning. So it depends completely on your system dynamics, like what particular tuning it needs. For mechanical systems, you can use the low pass filters to remove the noise before applying your D. So like the additional notes about it is your terms KP, KI, and KD. So these are the certain characteristics of them, like what you have to, like what it does and what not. So that we can term as, so we can say according to the characteristics table. So the closed loop response, that is the KP, KI, and KD, react to rise time, overshoot, settling time, and the steady state error in what consideration. So the KP, so KP, increasing KP generally decreases the rise time. Like the system, that means basically the system reaches the set point faster. Now about overshoot. Increasing KP typically increases the overshoot, causing the system to exceed the set point before settling time. It causes a very small change in set. About steady state error, increasing KP can decrease the steady state error, bringing the system closer to the desired set point, as we saw in the plotting or the graph earlier. About KP. So increasing KP generally decreases the rise time. And what we learned was when we see overshoot, we typically uh, introduce KI. So that is where we say that increasing KI typically uh, increases the overshoot. Settling time, it increases the settling time. Steady state error, so the primary role of KI is to eliminate the steady state error, ensuring the system eventually reaches the exact set point. And about KD, so rise time it causes a small change in rise time. Uh, and overshoot increasing KD generally decreases the overshoot, helping dampen the oscillations. And settling time, it decreases the settling time, helping the system stabilize more quickly. Now, it causes a small change in the steady state error. So, in the sense, tuning all three gains allows us to balance the speed, stability, and accuracy of a control system. So PID tuning. So why do we need tuning? So basically, so now the process of selecting the control parameters to meet given performance specification is basically known as control tuning. So which are very useful when your mathematical models or plans are not known. These rules can of course be like applied to the design system with known mathematical models. So basically, tuning is something where you can do it basic. And the most widely used method for tuning is the trial and error, where you keep on trying and resolving like to what all things you can do, like what all values you can add up to make the system quite stabilized and the desired output can be met. And so basically, that tuning at times you have to very fine tune it, so you have to start it with like incrementing it with 5 or 10 or 15, and then you have to go with points so that you can get the accurate value for the particular system to be stabilized. So we'll just have a look at a video where we can just see how you can tune a reaction wheel. So as we saw, like how we can tune the PID and how what values, like how we have to try and error for uh, doing that. Similarly now, so, so now talking about the real world applications. So there are a lot of real world applications where PID is being used right from your mobile device to your right from your mobile device to the car, the cruise control systems, to the drones, to HVAC systems where the temperature control is needed, as well as the robotic arms. So in real world, so the PID is used in a number of times. So wherever, like most of the applications where we use PID is used, talking about the more uses about it in the real world. So now we talked like about PID. So far we talked about PID as concept, but let's now talk about how PID, how it works in real digital systems like Arduino, Raspberry Pi, or industrial controllers. In theory, controllers work continuously, but in practice, we work with digital systems that take samples. They read the sensor values at regular interval. This is called as the sampling. For example, a self-balancing robot might take readings every 10 seconds. This regular time interval is very important. If the system samples too slowly, it will react. If it samples too fast, it may become noisy. That's why selecting the right sampling time is the part of design. So now, why the derivative term needs filtering? So the D in the PID, it stands for the derivative. It predicts how fast the error is changing. This helps smooth the response and prevents overshoot. But here's the catch. So the real sensors like gyroscope or encoders often give noisy readings. If the D-term responds to every tiny jump in the data, your system will be very shaky. To prevent that, we filter the D-term. In simple word, instead of reacting to like tiny movements, we look at a more averaged value. This makes the system more smoother and stable, especially important in like drones, robots, or the self-balancing systems. Now let's talk about the I part, the integral term. The part looks at how long the system has been wrong and adds up the error over time. But here's the problem. If your system is stuck or if something is responding, the integral term keeps growing and growing. Even when the error disappears, the item still pushes hard. This is called as the integral winder. To avoid that, we put limits on how much the integral term can grow. This is called as the anti-winder. Think of it like telling a controller, hey, calm down, don't keep pushing. If you're already faster and prevents overshooting. Now, we talked about how the PID is tuned, how we can tune the PID with trial and error. But in real world, like let's just see in real world how basically we can tune PID. So now consider, so you are in a room where you are listening to a music system, you are listening to music, and the noise and the speaker sound is too much. So and you have to basically adjust the bass, treble, and the volume of your speaker. So what do? You go there, you have the regulator where you just turn the volume up or down, turn the bass up or down, or similar things that you use. So you just play with the pots and you turn off the video, turn down the volume or turn up the volume. So basically, it is similar thing. So in theory, you can use formulas to find out the perfect values, but mostly in real life we started by tuning by hand. So you start by setting the integral and derivative to zero, so that is basically you introduce the proportional. So you just start with the proportional, and then you slowly increase the proportional gain until the system starts to respond quickly. But again, the overshooting comes into the picture. Then you add a bit of integral to remove the steady state error. Finally, you add the derivative to reduce the overshoot and oscillation. It's like it's as I said, it's like basically adjusting the bass and the volume of your speaker. So there is no like perfect setting for that. You just adjust it based on how it sounds. Similarly, the PID tuning is like part of science or part of art. So that's how it's done. And now talking about common situation where like PID fails. So of course it is not something that it always be successful. So the time delay. So if if there's a delay between you when you send a command and when the system responds, PID may act too early or too late. For like example, imagine a robot that reacts a second late by the time and the correction comes. It's already off balance. So now considering for this case, a perfect example would be a self-balancing board. So when it has to balance or the when it has to make its position upright, so a second delay would also matter, because of which it could fall and there could be misalignment in the path, which would result into the fall or the trip of the wall. Second is the changing systems. So let's say your robot works perfectly, like it's perfectly doing with the full battery and full efficiency of that. But as the battery drains, it starts behaving differently. So that is because the sufficient voltage and sufficient power it needs, it's not been, and that is where the PID doesn't PID would fail. That is because PID won't automatically adapt like whatever my according to the efficiency, it won't react or it won't be doing that. So that is where the PID would fail uh, in non-linear system. So some systems don't follow simple patterns. They might react differently at different speeds or temperature. That is where you can't use your PID. So, like beyond, so we talked about use of PID and all in this world, but the coolest thing about PID is it's not for the robots and machines. In fact, it's used in places that you won't even expect. So one of such places are your mobile phones. So it is used in your mobile phones to stabilize the movements. And in biology, it's used for the insulin dosage regulation, which is been used for the regular users of the insulin who are the diabetic patients. So also in finance, it is used to smooth out the volatility in like trading strategies. It is also used in manufacturing industries where you have to perfectly mix the chemicals. And no, coming
Uh, Sahil, we are able to see you, and I think we are able to hear you also. So if you say something. Can you unmute yourself, like Mike?
Hello? Yeah. Hello?
We are able to hear you now. Thank you.
Hello? Yeah. So we were talking about the advantages of PID. So the PID is the one which we can easily tune or easily use it, and it is basically an observation based tuning. So you can go for it, like you can see the changes physically and you can tune it according to that. Then you can use it. So it needs the value of variable what we want to control basically. But as you see, everything has some its pros and cons basically. So the disadvantages are like we cannot be sure whether the system is like controllable or like stabilized. So we need three variables need to be tuned for every controller. So considering your KP, KI, and KD, all three values have to be tuned if you are using all three together. And so yeah, you have to always look for all the ones, and you can't just go with just one of the values. You have to go with all three other values. So PID tuning is normally, as I told you, it is normally the hit and trial based one. So you can just go with like trial and error method. So you have to try with one value, it goes. If it's not done, you have to go with another value again. You have to change the values, keep on changing the values, and then when you find a stabilized output, then you're okay with that, and that's how you can tune one of them. So yeah. So again, some certain point like basic. So as we talked about the uses, so one of the most common use that we don't even know it is, but it's used in the camera to stabilize the images and stuff. So we can be using that into stabilizing it and solving. Yeah. So can after this, like, you can ask any questions if you have. Yeah, so the software which we were using right now, that was Copilot Sim, where we used a model. So that was basically a reaction wheel where we could tune the PID with that. Also, talking about other resources, so MATLAB, LabVIEW. So these are the some simulation software where we can be using it. So talking about how a PID controller plays and significant role in control system. So basically, it is used to regulate the system behavior, whether it is stabilizing the drone, controlling the temperature, or a robot to balancing a robot. So this is the first go-to solution, as we saw the advantages of PID. It is the most easiest way to tune, like, it is just a trial and error method, and so we can go with that. So okay, so efficiency of PID compared to others is like, it comes with it goes with like many other things. So if you go with the speed of response, so PID is kind of faster than other yes. So the difference between PID and NQR is the main difference is basically your PID can be tuned like a trial and error method. LQR is a mathematical or optimal theory. So for this, there is no system model is required, but for PID you need a full state space model to be used. You can manually tune KP, KI, KD. So, and in this, the optimization problem is billionaires. So healthcare solves the optimization problem. So method like there are many methods used in PID tuning other than manual tuning. That is Ziegler-Nicholas method or Cohen-Kuhn method, where you have to build the so basically talking about Ziegler Nicholas. So it in you have to keep increasing the cap, like similar the way you have to keep it is a mathematical model where you can solve the equation and find out the methods, find out the correct uh, answer to that. Okay. So the difference between singular Nicholas method and lambda method is basically, so it uses the system's ultimate gain and oscillation to set the PID parameters. And talking about talking about the K and KD, so it's where So basically, so what do you, the lambda tuning? It is the IMC. So basically, it is the internal model control. So the controller, which is like best for self-balancing or for advanced control. So it depends. So if you go with PID, so that is where you have to tune it, like manually tune it and see the changes, like what all things are being done. And according to that, it depends totally on the system dynamics, like what is being used and what not. So that is so yeah, about gain. So what gain? So yeah, in PID controls again refers to like each term. So like how it reacts to the error. So basically for like KP you called it as proportional gain, KI you called it as integral gain, KD you call it as derivative gain. Yeah. So yeah. So yeah, ZN tuning works for like order greater than order three system order systems, but like it is not ideally, or it's not ideal, or not neither, or we can say it's not much reliable for, as it causes instability or it causes large overshoot. So that are the reason. So in which case you have to use PID, PI, or so basically P and I you have to use where you have the systems which have the steady state error. PD is one where you need a fast and stable response, and PID is general purpose where you have to get a fast and stable response with removing the steady state error. And you can just use the proportional where the systems are stable, like stable by nature, or the simple systems. Mm, yeah, so basically PID seems to be a decision making, and also yeah, so RL and PID both are like kind of trial and error characteristics, both follow trial and error. So the only thing is like it, so basically you the tuning, like the main difference you go for is like RL goes for a model based, and so yeah, but the real question behind is like replacing the PID. Yeah, RL can replace in some cases, but like when you need a quick and reliable or a low latency control, then it RL won't be helpful. But like when, and also when the safety and explainability, like for in automotive or the medical where you can't take chances before, so that's where you can't replace it. And for like if you want to go with low cost microcontroller system, then like RL can be something that will be overkilling it. Is- What is exactly like how they are used in industry? Uh, like in the process industries, as I told you, in the chemical factories or like refineries or even the food processing plants. So the PID controllers are being implemented. So basically, it can be implemented in certain conditions like the temperature control or the flow control of particular water outlet, or the in a refinery is the oil outlet, the pressure and the speed and the level controls. And similarly, like how industries make PID tuning in their plant is just by like the method, or so they plan for it, like what will be the ideal conditions for that, and as per that. So LQR, how efficient? So it depends on the application. So it is a efficient for like basically linear or the model based control with, so with like a full state feedback, but it needs perfect modeling, which is not every time possible though. So, so you can term it as efficient, but it depends on where do you have to use that and where not. Yes, there will be a mix. So the basically the applications where you want like for smooth, faster, or minimal control, there you can use LQRs or the linearized inverted pendulum. So even it has been used in magnetic levitation trains and all. So thank you for the session. Thank you for attending the session. So we conclude the session now.